is to tee in where the main supply comes into the geyser. The second method is to replace a standard drain cock with a double drain cock. Both methods are acceptable. On a solar conversion, on the return side, there are also different methods. The one is called a long probe TP valve, and the other one is called a double port TP valve. Both of them are acceptable. Solar evacuated tube system is another form of solar water heating collectors that we get. Please give us some more information about these systems, some features and what they do.
Yes, Dion, evacuated tube systems are exactly what it's been called. The evacuated tube system has got a vacuum in between two glasses which has been put together, and inside the two is a vacuum. Vacuum is one of your best insulation that you get. What will happen is the heat will actually and the sun's rays will actually heat the glass, which has got an absorption area. That will then transfer the energy to whatever you got inside, a heat transfer sheet, water, or a copper pipe, and that heats it up. The vacuum then, the energy that's inside, cannot escape because of the vacuum that's between the two glasses, and that actually stores the energy, so your heat losses are very, very low.
I see on this one that you've picked up, there are 3 different colors. Can you give us some more information about that?
Yes, on the outer layer, you have what we call an anti-reflective layer. The second layer is what we call an absorption layer, and the third layer is a copper layer, which is the heat transfer layer. So your first layer will basically absorb or does not reflect your sun's rays or the heat or the UV. The second layer will absorb that energy, being transferred to the third layer, which is your heat transfer, that goes to your heat transfer sheet or your copper pipe or water that's inside your glass evacuated tube.
What are some of the major critical mistakes that people make when they install these systems?
The most important thing when you install a glass evacuated tube system, this comes in very, very last, once your system has been installed, because this is the energy that is going to be gathered. So once you've installed your solar system, you've done your pipe work, your plumbing and all of that, at the very last moment when you know everything is connected, you will then install your glass evacuated tubes when your system has been commissioned. So that comes at the very last point. Also very, very critical is when you use this is glass. So you must make sure that you always protect it, not to bump it or anything. Also at the bottom, you have a little thing that you can see here where the glass point is. And lots of people tend to put that onto the ground and break it. And when the vacuum is broken, the whole efficiency of the system is gone. That is the most critical part to maintain the vacuum in this glass evacuated tube. The other thing also that for customers to look at is that the minimum requirement from SAPs is a 2 millimeter thickness glass. So it's very, very important from your manufacturer that you purchase glass evacuated tubes at a 2 millimeter thickness glass, minimum requirement. Some companies also do a specification at 2.2 millimeters because there's a variance in manufacturing of 0.15. So if you manufacture 2 mil, it could be that your glass evacuated tube is between 0.8 or 1.85 to 2.15. So it's not a minimum at 2 millimeters. So that's very important. The glass evacuated tube, where at 2 millimeters, is tested through SAPs. That's why the requirement for any damage via hail. So it can withstand 35 to 38 millimeters of hail thickness. And they tested with a snowball air gun at 28 meters per second. So it can withstand very harsh hail conditions.
I see something like an aluminium that's inside these tubes. Can you give us what's the functionality of that?
Yes, the functionality of the aluminium that you see inside is the heat transfer sheet. This transfer sheet is very, very important. When you put it inside, like I said, the third layer is the heat transfer layer, which is made out of copper. That transfers the heat to the aluminium heat transfer sheet that transfers it to the copper pipe that's inside that heat transfer sheet. So it's very important that that heat transfer sheet touches all around inside the glass evacuated tube. Otherwise, it will not work. So it's important to make sure that this sheet is at a very good quality and that it covers that areas to transfer the heat most effectively.
I see we have a cut-through demo version of a manifold. Can you please give us some more information in terms of How does the water flow through this manifold, and how does it function in terms of heating up water?
Yeah, the manifold acts as a heat exchanger. Basically, your glass evacuated tube with the transfer medium that's inside are connected to the manifold. The manifold itself, you have water comes in at one point and it will enter at the other point. That transfer medium that is connected to the manifold will transfer the heat to the water that runs through the manifold that goes to your geyser. So it's very important your transfer medium that is being connected correctly work together with your glass evacuated tube, and then your insulation of your manifold is also very good to minimize your heat loss in the manifold.
Are these copper probes in contact with the water?
No, the manifold and the vacuum tube, the transfer medium that's in the vacuum tube does not get in contact with the water that runs through the manifold. The manifold is a heat exchanger. So physically, the transfer medium that you got in your vacuum tube slots into the manifold, and the water will then get heated up by that transfer medium. When there's a problem on the vacuum tube itself, you can actually remove it out of the system, and the manifold will have no leaks. So there's no water contact between the vacuum tube transfer medium and your manifold.
Are there any specific reason why these tubes are round?
Yes, the reason why it's round is it actually covers from early morning to very late in the afternoon the sun's rays. As the sun comes up, it catches it from an angle till very, very late. Also, when it's round, it's easy to clean. So when you have any dust or anything on it, it can wash it off easily.
Apart from the supplier specification, what are the factors you should consider when you decide what size system you will apply to the water capacity?
The sizing is important. The radiation in Uppington is much higher than the radiation in Durban. In Durban, you might use an 18-tube collector, where to the same energy output, you will use a 12-tube collector in Uppington. The second point, which is important, is the hot water usage per household. You might have a 200-liter system, but the usage between two people that only stays there could only be 100 liters. So you just need to heat up 100 liters.
The factors to consider is radiation, volume of water that you want to heat up in conjunction with the utilization of water. Then when we install an evacuated tube system like this, what are the things we should be looking out for? How do we fasten it, and what is important to look at?
Dion, there are obviously various different types of roof structure. You get thatch, which we don't recommend that you put something on directly onto the thatch. You get corrugated iron, you get Harvey tile, you get Corex board. What we're working with today is clay tiles. And really what we need to do is we need to make sure that our frame is secured on the roof so that it doesn't move. The way that we do that is we'll put hoop iron or strapping iron onto the frame at the bottom. We'd lift this tile, slide the hoop iron underneath it into the roof where we've got our workers inside the roof. They would then take it and put it over the brand ring and secure it to the brand ring. You do the bottom side first, and then you go to the top side. And if you have a look carefully here, you will see that we've already secured the brand ring and pushed it underneath the tile. Securing it inside is more where the challenge is, but we need to make sure that it is secure so that it cannot move, especially in coastal areas where you have high winds and things like that. So it must be very flush. Any drilling that needs to take place, because you might have some systems that actually come supplied with feet. But always remember, if you're going to then drill on a tile, you must drill on the ridge of a tile and not in the valley, because otherwise you're going to get water running down the valley and you're going to get waterproofing problems where you're going to have leaks going into the actual roof. But make sure that your frame is lined up straight before you do any drilling. Make sure that everything is in place, and then slide it underneath the tiles.
What about the tubes? Can we start off doing it right now?
Dion, if you do that, you are going to get seriously burnt hands. The tubes is the very, very last thing that you actually do. Do everything before that. You install your frame on the actual roof, you make sure that it's connected, you do all your piping, you do your pressure testing. The very, very last thing that you do is you install the tubes. It's a dry connection. There is no water going in the tube, so you don't have to put it in. And we'll get to the tube installation in a while, but those tubes, don't leave them in the sun. They generally are supplied in a cardboard box with nice styrofoam packaging, and even with that styrofoam packaging and in the cardboard, leave them in the shade. If they happen to be out in the sun, cover them, make sure that they're not exposed to the sunlight, because there's nothing worse than working with really hot copper.
Thermosiphon systems. There's a couple of things we should be looking out for. What are those?
Thermosiphon works on the natural principle of hot water rising, cold water sinking. So when you're doing your piping, it's critical that you actually get your angles correct. You cannot have a downward angle or an upward angle coming out of your geyser. Downward angle out of the panel, upward angle out of the geyser. It must flow down. So in other words, what we're doing is we're heating up the water here in this manifold. As the water heats, it'll want to rise. It's got to be able to flow naturally up and into it. And if you have a look carefully here, you'll see that there's an angle that is not higher than that angle. The hot water wants to rise. It'll naturally want to climb up into the actual geyser. Critical is the angles that we actually have. Now you need to have a 30 centimeter drop between there and the actual collector. Not 30 centimeters across and 30 centimeters up. 30 centimeters vertically must be the distance between the manifold and the actual panel. So absolutely crucial is you've got to have an upward flow from your collector into your geyser. You can't have a dip coming out of your collector, and you can't have a rise coming out of your geyser. That flow is absolutely critical.
Glenn, does the thickness of the pipe play any role?
Yes, it does. But because it's a natural process, it'll always rise when it is hotter. So the thickness is not as crucial as in a split active system where you've actually got to force or control the rate of flow going over the actual elements. As this water gets hotter, it'll want to go up, and the denser, cooler water will want to drop down into the collector. So you'll have a flow on this side going up, and on the other side of the geyser, you'll have a flow coming down into the collector. And this will be your circulation loop.
I see you still haven't put in the pipes.
I don't want to burn my fingers. I haven't even connected the main water to this. All I've done now is created what is called an open loop, because this is a direct system. So I've created an open loop between the geyser and the actual manifold. The next process that we'll go through is connecting the water mains to the cold water in supply and the hot water supply to the house.
Are there any risks in terms of freezing?
The natural process of hot water rising, cold water sinking means that the hottest water will always remain in the actual geyser. At night, this manifold is going to get cold, but it's very well insulated in that it's got rock wool or iron wool, and it's only got about 2 liters of water inside it, so it's unlikely that it's going to freeze. Even if it does freeze, it's not going to destroy the system at all. We've connected our mains water pressure to the actual geyser. We've connected our hot water supply from the geyser to the house. We've pressure tested everything. We have no leaks. And the last step in the whole system is to put the glass evacuated tube into the actual solar panel. The very first thing that we do is we apply thermal paste to the condenser. Put quite a nice liberal amount of thermal paste on each of the condensers. Spread it around so it is covering it nice and efficiently. This paste helps to transfer the heat from the condenser to the copper in the manifold. The next stage is to get yourself some water mixed with dishwashing liquid to lubricate the rubber seal. Make sure that you give a fairly liberal dosing of dishwashing liquid and water. Get your tube and lubricate the outside top portion of the tube as well. Next part is absolutely critical. Make sure that you get the copper piping and you pull it out of the actual glass evacuated tube to give you some leverage. Line up the condenser with the hole in the manifold and insert it until you hear an audible click, and then you can slide the glass evacuated tube up to the lining and gently twist it until it's all the way in. We've now put the glass evacuated tube into the collector manifold. The last portion that we do is we slide on the holder, clip it into place, get the cap, and making sure that you don't cross thread it. Screw it in so that it holds the glass evacuated tube in place. Don't over tighten it. All this has got to do is just keep the glass evacuated tube in place. And that's how you install a glass evacuated tube. Just bear in mind that these clips at the bottom might vary from system to system. Some have a clamp where you've got to tighten it. Make sure that you don't over tighten it with a screwdriver. Some just have clip-in systems. They're generally pretty self-explanatory. But the critical thing to make sure that you have is heat thermal transfer paste, so that you can transfer the heat from the condenser into the manifold, and make sure that that copper rod is securely installed in the manifold. There we have it. That's the final step of the Thermosiphon system.
So Glenn, we've completed this Thermosiphon installation. Always remember that the geyser must be installed according to SANS 10254. Always make sure that the site is nice and tidy, there's no things lying around, and that all safety precautions are being taken while on site.
Absolutely, Dion. You raise a very important point. The SANS regulations are there to protect the homeowner, to look after the people, to make sure that the users don't get scolded. So it's imperative that we actually make sure that all the safety valves are in place, the air release valves are in place, and everything is done according to regulations. I'm very happy with our installation today. I know the system is going to work exceptionally well.
Glenn, on the flow side, there's a lot of things we need to take cognizance of. What are those?
Well, obviously, the very first thing that you've got to have a look at is make sure that you've got a pressure valve that matches the pressure that the geyser's rated at. This is a 4-bar pressure. We've got a 4-bar pressure valve going in here. Your vacuum breaker 30 centimeters above the level of the actual geyser. That's on your mains inflow into the actual geyser itself. From your geyser to your panel, we have the heat trap on the side, which then goes to the pump, which circulates the water up through the roof into the solar collector outside on the roof.
Is the direction of the pump important?
Obviously, it's very, very important. We want the flow to come from the geyser up through the pump, out onto the roof, and to be deposited on the other side. So this is a one-directional pump. In other words, the flow must go this way. We have a one-way valve as well as the pump, which ensures that it goes in the correct direction.
The function of the one-way valve?
To make sure that you have your flow going from your geyser up through the panel and not reversing down from the panel down into the geyser.
In terms of the probes, I see you've got the probes again here at the geyser.
This is our T2 probe, which is connected into our controller, which we discussed a little earlier. T2 measures the temperature of the water in the geyser at this level. When this is 8 degrees less than the temperature in the controller outside on the roof, it will then turn the pump on. This pump will then draw water from your geyser, push it up into the manifold outside on the roof, pass it through the manifold. As it passes through the manifold, it absorbs the heat and gets deposited back into the actual geyser. So T2 controls the temperature differential between the manifold and the actual geyser.
Is it then correct to say that the flow side is the so-called cold side of the whole equation?
Dion, it is the cold side, but it's not cold. It's cooler than the hot side. Your cold inlet is your municipal mains, but what we are doing is we're taking warm water from the geyser, pumping it through the collector, heating it up even hotter, and depositing hot water back. So yes, it is the cold side of the flow, but it is not cold.
On the return side, I see there's a couple of things we should take note of. What are those?
Well, Dion, the very first thing that you'll notice is this little kink that we have in here. It's the heat trap. Because of the normal process of hot water rising, cold water sinking, overnight this geyser is still going to remain hot because it's got nice insulation around it. But the panel that's sitting outside on the roof is going to cool down. Now that water is going to become denser and cooler, and it's going to want to sink down. So it is going to come down the pipe and try and get into the geyser if it can. But cold water can't climb up a hill. So it's going to go to the lowest point, which is here. Similarly, the hot water that's in the geyser wants to try and escape and get up as high as it possibly can. Now the maximum height that that's going to get to is to here. It will not then go downhill and then go along the pipe and go uphill again. So just to reiterate, the hot water will get to the maximum height of here, and the cold water will sink to this lowest level over here. That's the first thing. The second thing is obviously in terms of our SANS regulations, we've got to have a temperature pressure valve, and the exterior pipe has, well, the pipe from the pressure valve has got to go to the exterior of the house. The third thing that we're looking at is our connection here. Here we have our T3. When we did the controllers, we actually put in the T3 into here. It measures the temperature at the top of the tank, and that's the T3 probe that controls the element in terms of when we switch on the power to the element to heat it up overnight, let's say at 3 o'clock in the morning. So those are the three things: your temperature pressure, your temperature probe going into the actual geyser, your TP valve, and your heat trap.
Glenn, we now have completed all the components on the return side, except for this last step. So just tell me, what is that and why is that important?
Dion, this is an air release valve, and it is critical to the whole system. Because the manifold gets so hot, it builds up pressure. As you know, hot water heats up. As it heats up, it expands, creates pressure. If you don't have your power to your circulating pump for whatever reason, whether it be a DC pump or an AC pump, but if there is no power to the pump, it cannot circulate the water. So this is going to start getting hotter and hotter. As it gets hotter and hotter, it builds up more pressure. That pressure is going to go along the pipes and eventually find a weak link and create a burst. This air release valve here is critical in ensuring that we actually release that pressure. So if the water starts steaming in here, it'll expand, and through this valve at the top here, the steam will actually dissipate out. Critical, when you install, make sure that this dust cap is actually loose. It is not tight. If it is tight, then the air release valve cannot work. So it must be loose. Make sure, as a last stage, that you actually loosen that dust cover.
So Glenn, what you're saying, this is actually a safety measure.
Absolutely, Dion, and it's absolutely critical because without this, the geyser or the water in the manifold is going to heat up and expand. And as it expands, it creates more and more pressure. That pressure has got to escape somewhere. And if we don't have the safety valve up, somewhere it's going to blow and you're going to get hot water all over your ceiling.
How do we minimize the use of electricity in a solar installation?
Dion, that's a very important point. If we have a look at the normal functioning of an electrical geyser, you have a hot water outlet. So when you turn on a hot water tap, hot water is going to come out. It then gets replaced with cold water going into the actual geyser. That cold water is measured continuously with a thing called a thermostat. That thermostat is set to turn on the element when the temperature in the geyser drops below a certain point, let's say 50 degrees. So with cold water flowing into the geyser, the temperature, the ambient temperature in the geyser is going to drop. That is going to be picked up by the thermostat and automatically the element is going to be turned on. We don't want that to happen. We want the sun to heat the water, not electricity. So we've got to actually change the controller. So the very first thing that we do is we remove the electrical thermostat that is supplied with the geyser and replace it with a thermostat that is supplied with our controller. This thermostat now will only supply power to the element when we require it. So it will not turn on automatically, thus reducing our use of electricity.
Then is the location of the probe important in the manifold?
Yes, Dion. Obviously, we were trying to minimize the use of electricity. So if we've done our job correctly and we spec the solution correctly, hopefully the manifold will get the temperature of the geyser up to around about 55 to 60 degrees on a daily basis. However, we might have some cloudy, inclement weather for 3 or 4 days in a row, in which case the panel would not be able to achieve those sort of temperatures. So there we need the element to actually kick in and assist us. But the idea is to actually only